Hello everybody, and welcome to page 139 of the workbook. This is the beginning of section 20.1, and chapter 20 is the last chapter of your course. And the theme of this chapter is to introduce two of the big theorems of multivariable calculus. One is called the divergence theorem, and the other is called Stokes' theorem. And both of these theorems have something to do with measuring the flow of a vector field through a surface. You remember back in chapter 19, you came up with all kinds of formulas, different ways of measuring flow through a surface depending on what the surface looked like. And one thing you might have noticed is that those problems are rather tedious in a lot of cases. The formulas are long, there's a lot of algebra to do. And so what these theorems are going to do for you is to make it a lot easier to calculate that flow in a couple of specific situations. Okay, so before we can get to the theorems, we need a couple of concepts. And the first of those concepts is the idea of the divergence of a vector field. Okay, so divergence is about outflow of a vector field. And to illustrate that concept, let's look at the two vector fields down below here, so you can see the two pictures. And in both of those vector fields, I'd like to focus at the point at the origin. Okay. So for the field at the left, you might notice that all of the vector field lines are pointing away from the origin. So word that we could use to describe it is that the origin is a source in the case of that field. We've got positive outflow away from the origin. Okay, and then the field over to the right, exactly the opposite situation if we look at the origin. Okay, there, all of the vector flow is going into the origin. Okay, so we would call the origin a sink. And we would say that there's negative outflow because of the fact that there's inflow to the origin. Okay, what we'd like to do in this definition below is to kind of quantify this idea of divergence. How would we specifically define it? Okay, well, here goes. This is a little bit of a complicated definition, so we'll think about it in pieces. So the divergence, or the flux density of a vector field, okay, at a point is given by, here's going to be our notation for it, so div of f at xyz. And to help you picture this, imagine taking a point. I'm looking at the picture over here to the right. So a point xyz. We're going to draw like just a tiny little sphere around that point, and we're going to start by taking the flux integral of f over the sphere. So that's going to measure the flow through the sphere. Okay, then we're going to kind of normalize that. So we want to take that flow and divide by the volume of the sphere. And then we're going to do one last thing. We're going to take the limit as the volume of that sphere goes to 0. Okay, so the fact that we divided by volume tells us that we're really talking about flow density, the flow per unit volume. And this limit that we added at the beginning is a way of contracting this quantity that we're measuring to a single point. So we're measuring the flux density of our vector field out of a single point. All right, and one last thing you might notice with this definition is that we give the sphere the outward orientation. That guarantees that this divergence is positive if there's a net outflow. That's kind of what we want to mean by divergence. Okay, so a couple of notes that we can make. Okay, starting with the first one here. Okay, so first of all, the sign of the divergence. The divergence is going to be negative if there's net flow into a point and positive if there's net flow out of the point. Kind of the same idea as what we saw in the two vector fields at the top of the page. Okay, and another comment we could make is that this definition that we wrote up here is a nice way of kind of picturing what's going on with divergence, but it's not a very practical way to calculate it. Okay, so there's an equivalent way of thinking about divergence that's easier when we're doing calculations. That's what note number 2 is about here. Okay, so imagine that we have a vector field broken up into its three components, f1, f2, and f3. Turns out that you can calculate the divergence using this formula. notice that it's just a sum of partial derivatives, one for each coordinate and one with respect to each variable. That's equivalent to the definition that we made up here above. Okay, and that's called the coordinate definition of divergence. Okay, and I want to close this page by just making one notational observation. That's note number 3 here. There's an alternate notation for divergence that's kind of convenient. If you're a physicist, you may very well have seen this notation before. We can write down divergence shorthand by writing this, del dot f. That upside down triangle is the del operator that we introduced back in section 18.3. Let's remind ourselves what that was. So del was just kind of an empty operator of partial derivatives. So it's like a gradient without a function. Okay, and then f, of course, is just our vector field, so with the 3 components. And so what would del dot f mean? Okay, well, remember how you ordinarily take the dot product of 2 vectors. It's about taking the corresponding components and multiplying them together. In this case, it's not exactly multiplication, it's more application of the derivative to the components of the vector field. But here's what we're going to get. If we kind of follow the suggestion of this notation, del dot f, we're going to just take this component-wise and we're going to apply partial x to the first component. That's going to give us partial f1 partial x. Apply partial y to f2 and so on. And notice that that gives us exactly the same formula that we have up here. Okay, so del cross f is just kind of a nice shorthand way of remembering what that formula says.